Hello friends, so today we are going to solve 3 questions, and all these 3 questions are from statics. So the first question, it is given that 3 different thin planar objects in form mass density rho are placed one at a time between 2 identical smooth frictionless circular cylinders of radius r. In each configuration, the line joining the centers of the cylinders to the contact points with the object make an angle of theta with the horizontal. A horizontal compressive force F is applied to each cylinder so that pair remain in contact and hold the objects in equilibrium. For each elicited space, find the magnitude of horizontal force expressed in the terms of rho object dimension r theta g if needed, required to keep the 2 cylinders together. Determine also for what values of theta the required force is maximum and minimum. And we are given 3 shapes here. First shape is an isosceles triangle whose 2 equal sides have length L and whose base is horizontal. Shape B, a rectangle of height L measured vertically and width W. You may keep W symbolic, give the answers per unit width if convenient. And part C, a circle of radius A in the plane of the figure. So we have 3 shapes rather. Okay. And we are going to solve them one by one. So let us take part A. And in part A we are given an isosceles triangle and that is placed on a okay, first of all, because in all the objects in general are placed in between the cylinders. So this is a first cylinder and this is second cylinder, and the objects are placed such that they are touching both the cylinders. Okay, so it means there will be 2 points of contact. Let us call this as P1 and this is second point of contact P2, and that will be true for all the 3 shapes that is mentioned in the question. Okay. Therefore, we can say that there will be 2 normal forces that will be, so this is the first one and this is the second one. Okay. And we are also given that it is making an angle of theta with the horizontal. Okay, if O1 is the center of the first one and this O2 is the center of the second one, so this angle will be theta, and similarly for the other part also. Okay, so it will be true for the second one also. So let me draw this, because normal, so this is a normal 1, okay, and this is a normal 2, and once again this angle will be theta. So this is true for our all the figures. So we are going to have 2 points of contacts for all the this. Okay. Therefore, we can write that we having 2 contact points independent of shape, and these 2 contact points we called as P1 as well as P2, and 2 forces that is applied which are the compressive force. Okay. So these are two forces, and these are F as well as F. So this will be common for all the figures. And we are given that rho is the uniform mass density. Therefore, in general, we can say that mass density is given as rho. Okay. And for the sake of convenience, we assume that the object, or we can say this object area is A. Okay. Therefore, we can write that the mass of object will be equal to m, and that will be equal to rho multiplied by the area. And like I said, we have having a normal. So suppose this is our point P1, and this is our O1, and this is our normal N, and this O1 is making a angle of theta with the horizontal, and therefore we can divide this normal N into two components. So this angle will be also theta, so this will be N cos of theta, and this will be N sine of theta. And this will be true for our both sides, P1 as well as P2. And in the downward direction, we are going to have its weight, that is called W1, and that will be true for the second part also, that is our W2. So we can write that for vertical equilibrium, we can say that our 2n sine of theta is equal to m times g. Okay. And from here we can write that value of n will be equal to our mg, and we have our sine of theta. Okay. And for our horizontal equilibrium, we can say that the force on each cylinder will be equal to n cos of theta, and we can substitute the value of n. Therefore, we get the F each will be equal to, we get this as mg by, 2 is missing. So we get this as our mg by 2, and that will be our cos of the cot of theta. So this is the force of our each, and total force, total horizontal compressive force, and let us call this as Ft, will be equal to twice F each. We substitute of F each, we get that our F total will be equal to 2 times mg by 2 cot of theta. 2 and 2 cancels out, so this comes over mg, cot of theta. And so this will be always the compressive force, and it is going to change only based on our mass, okay, or we can say our area, because we know our mass is dependent upon our area. If the area is changing, the mass is going to change. Obviously shape is changing, so area is bound to change. So let us consider one by one. So we have our part A. And in part A, we are given that our this isosceles triangle is given. Okay. Therefore, we can say that so we are having an isosceles triangle, and it is given as a inverted isosceles triangle. Okay. So we can say for part A, we are having isosceles triangle, and so the isosceles triangle is given that the base is horizontal, so the triangle will be something like this. And okay, let me draw the cylinders first. So this is our first cylinder, and this is our second cylinder, and in between we are having the isosceles triangle, so it will be something like this. Okay, so this is the isosceles triangle, and so this will be once again our P1, and this will be contact point our P2, and the length of this isosceles triangle is given to us our L. So this is our L, and this is also our L. So the angle, this angle will be coming equal to our 2 theta, okay, because we have radii and they are making contact point as the angle theta is given with respect to horizontal. Therefore, if B is this base length, therefore we can say that our we have the base length, and that is our B will be equal to 2L sine of theta. And if we consider that the height, and suppose that is given as h, then this h will be equal to L cos of theta. And now we can easily calculate our area of the triangle. So we can see the area, and that is our A will be equal to our half base into height, and this comes as our half 2L sine of theta and L cos of theta. So this 2 and 2 cancels out. Okay, so therefore we get our area A will be equal to our L square, and we have this as sine of theta and cos of theta, and we can write in terms of our trigonometric identity L square, and this will be sine of 2 theta. So this is the area in the first case, and from here we can easily calculate our mass, we know that our mass m is equal to density multiplied by area. We have already written the formula at the start. Therefore, we get this as our rho, and we have our half L square sine of 2 theta. Therefore, we can say that our F total will be equal to twice, and we already know it is given as mg cot of theta. So we can substitute this m is our rho 1 by 2 L square, and let me open this again. It will be help to solve this. Sine of theta cos of theta multiplied by cos of theta upon sine of theta, because that was cot, and this 2 sine and sine goes away, and this gives us that the total compressive force at f of t will be equal to our, this is our rho L square, and something is missing, G is missing, and let me put it here, multiply by G, rho L square G, and we have cos square theta. So this is the total compressive force in our first case. Okay. And we come to the next part, and the B part, it is also find out the maximum and minimum value for our theta in each case. So let us solve it. And this we found out F total. We can also write the formula for our F each. Then this F each will be equal to our rho G L square by 2, and this will be our cos square theta. And so we just differentiate it with respect to theta, and we get this as our df each upon d theta will be equal to rho G L squared by 2, and this comes as 2 times cos of theta and minus sine of theta. And here this 2 and 2 cancels out. Therefore, we can say that our derivative of our f each divided by d theta will be equal to minus rho G L square, and we can write this as 2, and this comes as a sine of 2 theta. And we put this derivative equal to 0, okay, because we need to find out the maximum minimum. So we put equal to 0, therefore we get that sine of 2 theta is equal to 0. Or in terms of trigonometric identities, we can say that our 2 theta is equal to over n pi. Okay. And or if we take the interval, for our theta less than equal to pi by 2 and greater than 0, and for these two interval, we can say that theta will be 0 or theta will be equal to over pi by 2. Okay, and we can put this later on also. And now we find out the second derivative. So we get second derivative is equal to, this comes as minus G L square, and we are going to get this as our cos square theta minus sin square theta, or we can sort it out. We can write this minus rho L square, and we have cos of 2 theta. Now let us substitute the value of theta is equal to 0. So we can say at theta is equal to 0, the double derivative will be equal to our minus rho G L square, okay, which is less than 0. So it means we are going to get a maxima, and at theta is equal to pi by 2, we get its double derivative theta square will be equal to plus rho G L square, which is greater than 0, which will be giving us a minimum. Okay. And I think we need to find out the value also. Okay, determine for what values. Okay, so we need to only find out the value of theta. If required, we can find out the value. It's not a big issue. We already know the maxima, minima. We substitute it and we get the values. Okay. Now we come to part B. And in case of part B, we are given a rectangle. So we have two cylinders which are in contact with each other, and the cylinder and the rectangle is placed something like this.